This is the fifth lecture of our course. It is entitled Nijenhuis Geometry. It is dedicated to this new branch of mathematics we have been developing, me, Alexey Bolsinov, and Vladimir Matveyev, in a series of works. You've already listened to the first chapter of our course, which consisted of 4 lectures by Alexey Bolsinov. You were introduced the basic notions of the Nijenhuis geometry we deal with. We deal with primarily operator field with a vanishing Nijenhuis torsion. And this operator field is started from the point of view of geometry, not algebra. This is important distinction for our science. So what we will do today, we will prove several theorems concerning the local structure, and we also introduce the Haantjes tensor, Haantjes torsion, and this part is important because Haantjes geometry is a very close cousin of Nijenhuis geometry. They are developing side by side, and different mathematicians, they have different opinions on what is more important. We think Nijenhuis geometry is more important, more basic, because you can study objects easier, but some think that Haantjes geometry is more fundamental. It doesn't matter which one is better, because they both constitute to the knowledge of the geometry and integrable systems. So the facts we will need today is the ones we will have to recall. One is called from the general course of ODE, or probably from the previous lectures. So the first fact is called straightening theorem for vector fields. It is the basic fact about vector fields, which states that given a single vector field which is non-zero at a given point P, you can take a coordinate system with the first coordinate vector field being the vector field psi. It is a basic theorem. It is usually proved in the course of ordinary differential equations because vector field in local coordinates is nothing but a stationary system of ODE, which means the right part does not depend on the parameter t. So what it says that in appropriate coordinate change in non-singular points, you transform the given ODE to the simplest one. The thing here, this theorem is quite important. It is a basic, it is foundation of the idea that you need to study in vector fields, not the regular points, because they are simple and you cannot distinguish one point from the other in terms of coordinate systems, but you need to study singularity. The second fact is a corollary of the Frobenius-1 theorem, which was proved, I think, in lecture 2. This Frobenius-1 theorem states that if you have a commuting vector, that you have a collection of vector fields and you can make them coordinate vector fields if and only if they commute and linearly independent. We need one part of this theorem, which implies that if you have k vector fields, then and they are all linearly independent at one point, it will be most of them facts we deal them in local coordinates, which are centered at point P, which is important. We will mention that in the statement of the theorem, and sometimes we do, sometimes we don't, but we will mention if it's not assumed. So you need to keep in mind that we assume that coordinates are centered at point P throughout this lecture. You see that you have a linearly independent vector field, vectors at a point, which means that locally vector fields are also independent, and they should commute. If they commute with respect of standard commutator of vector fields, then you have a coordinate system which with two kinds of coordinates. One part of coordinates from x1 to xk are the ones that correspond to the basis vector fields for our psi, and the others are the ones that do not. You can understand them as integrals of the xi, because if you apply xi to y, you get 0. So you see that this collection of functions have a common integrals, right? So they do have a nice foliation behind them. This is an important theorem. You can see that the second part is some sort of generalization of the first part. See, you can think about the second fact as about the fact when you straightening several vector fields. This idea will be useful later for us. Okay, we start with a classical theorem, Nijenhuis theorem. This is the theorem he proved in his work in 1951. Actually, I should make a remark. You see, at that time, if you look at his work, there are a lot of statements. They all are proved, but not all of them are formulated as theorems. Most of them statements in this article, they are formulated as a plain text. So if you will go to this article and try to find this statement, you probably will have some difficulty, because you'll have to read through and find the place where Nijenhuis, which was solving totally different problem. We will discuss it later. When he aforementions that if his tensor, which is Nijenhuis torsion, vanishes, then the operator can be brought to the following form. So in this, in this lecture, we deal primarily with real eigenvalues, and that's what we will do. And we start with a basic result, which is well known to everybody. It's a common knowledge in differential geometry. It sounds like this. If you have a Nijenhuis operator, you should be familiar with the term, means that Nijenhuis torsion vanishes. With real pairwise distinct eigenvalues, it means eigenvalues are distinct, and from the point of linear algebra, you have what's called a simple spectrum. Then there exists a coordinate system in which the operator can be brought into to the following form. The form is diagonal. You have functions on the diagonal, but important part is that each function depends on its own coordinate. See, lambda 1 depends on x1, lambda 2 on x2, etc., etc. The characteristic polynomial of L at a point P is factorized. It can be factorized. This is the proof. Proof uses splitting theorem. I didn't put it into the facts because I think splitting theorem is the thing you should all remember because it's in our course. So we will refer to this theorem quite a lot. It is a very important tool in constructing the geometry locally and sometimes globally. The characteristic polynomial of L at point P is factorized like this. So you see that at point P, all the eigenvalues of the characteristic polynomial have multiplicity 1. They all are single functions. They all have single multiplicity. So you basically split your characteristic polynomial into the product of linear polynomials, which is a good sign, because in this case you can, what the splitting theorem says, it says that if you split a polynomial at a point into some polynomials, then you can split the operator structures. Here we have one-dimensional polynomials. We have splitting into one-dimensional distributions. One-dimensional distributions are always integrable, so we get the theorem. Here it is. This is just the application. You see how easy it was to get the classical theorem from the fundamental splitting theorem. Again, splitting theorem is important. So let's proceed to the normal form. In mathematics, normal form does not have a strict mathematical definition. It is usually defined depending on the context, right? So if we deal with vector fields or we deal with any other geometric objects, it is natural to ask, what is the normal form of this object? For example, if we talk about symplectic structure, the normal form is given by Darbuth theorem. It says that the normal form is unique, right? If we deal with a flat metric, again, we know that the normal form is also unique. You have one standard matrix. It has ones and negative ones on the diagonal. So basically, you have different metrics with different signatures. So the natural question in Nijenhuis geometry is, what is the normal form of Nijenhuis operator? You see, this question is quite complicated, because if you deal with a matrix of forms, which means covariant or contravariant tensors of rank 2, right? It has either two upper indices or two lower indices, right? Even in regular points, operators, they have a richer geometry. They have a richer algebra first at point, right? You have Jordan normal forms, you don't always have diagonalizability. So it is expected that the question of normal forms for Nijenhuis geometry will be much, much richer, much, much complicated. It will be way more complicated than in case of, for example, symplectic geometry. This is, in fact, what happens. We start with the simplest normal form. We will proceed to the more complicated normal forms later. This is, by the way, is a large part of our course, because different normal forms, they play different roles in different branches of both applications, finite and infinite dimensional. Doesn't matter. So we ask, what is the normal form in case of diagonal operator? Okay, let's look at coordinate system. We know that operator is transformed like it is written in the first formula on the slide, right? You multiply it by dx over dy stands for the Jacobian matrix, right? So it basically matrix n times n consisting of partial derivatives of x by y. So it is transformed like this, multiplied by inverse of the matrix and then matrix on the other side. Okay, when we want to ask the question about normal form, we want the normal form to be diagonal. Okay, this automatically implies, because the lambda 1, lambda n, they both pairwise distinct, it automatically implies that Jacobian matrix is diagonal also. It is a simple exercise from linear algebra to prove that this is the case. Okay, then we have a coordinate change in the form xi depends only on yi, see? And we see that the coordinate change according to the rule of transformation, because this is only part of the transformation. When you transform a tensor in local coordinates, you first apply the Jacobian matrix, and then you need to substitute the coordinates into the tensor itself. We see that in new coordinates, in coordinates y, right, we have the transformation goes like this. We just substitute into the lambda the x depending on y. And we see that this substitution is independent in each term, in each eigenvalue. So we have eigenfunction, right? And we substitute the coordinate inside. What is the result? This is what we trying to describe, and what we have just described is the freedom we have in choice of coordinates, because when we choose diagonal form, there are a lot of different diagonal forms we see, but we need a normal form. Normal form should be unique. We should be able to pick exactly one form for the given collection of eigenfunctions. So we arrived to the following problem. That's what we started. We are trying to investigate, and we're applying the resources we have. And the first what we can do is we see that we give a following problem. I have a function f, and I'm trying to find its normal form. It means that I substitute instead of x depending on y with a property that derivative of x does not vanish, right? It's not zero. So I substitute into the f, and I ask what is the result? What is the result that I can get? For smooth functions, it is a complicated problem because you have flat functions. But in analytic case, this problem can be solved, and most of the normal forms we will be dealing in this course, right? They are from analytical category, because we will have sometimes we will deal with systems of PDEs, and you need a theorem which ensures that they can be solved, which is Kavalavskaya Theorem, so Kavalavskaya Theorem, if we are being precise. So we proceed, and we see that the following proposition holds. So go back, see what we're asking is, what is the normal form of a function? We reduced the question for the Nijenhuis operator, for the large object, to the rather specific analytical question. What is the normal form of a function if we allow substitutions? Okay, the normal form of a function is governed by two facts. First of all, we assume that the function is not constant. This is important. We will see it later in the comment, but for now we assume that it's not constant. If it's not constant, right, it changes over x. When x changes, we get the following. We see that the function can be brought to one of the following three forms, right? The forms we see, they are obtained easily. Look at the proof, how we prove it. We just take fx minus c. We get a function which vanishes at the point P. Again, all the coordinate systems are on point P. If it vanishes at the point, we have a thing called the order of zero, which is the maximal power of x. You can divide this function, and for the function to still be analytical. In other words, you have decomposition of f of x into the series, converging series. This is the analytical function, and this is the first non-zero term. See, a is not zero, and k is the first non-zero term. We see that here we use that the function is not constant, because if it's constant, there are no such terms, so they all vanish. So we take that, and we perform the following changes. It looks, we take a model, but it seems like it's a bad idea. We also take a root, right? We take it into the power 1 over k, which is taking a kth root, which seems like a bad idea, because in general these functions are bad, but they're bad in the in different region. So over here they're okay, and they're analytical functions. So this formula, which is in our case in some neighborhood of the origin, is analytical. This provides the coordinate change. Now we see we need to one more observation, because we didn't need this preposition as it is. We want it, again, we keep in mind that we are investigating the normal forms of the Nijenhuis operator. So what we need to get this thing going, right? So this proposition is valued for us only in terms of this investigation. So we look and we note that if k is odd, right, like 1, 3, I don't know, then this coordinate change is unique. If it's even, then this coordinate change is not unique. You can multiply the coordinate change by plus or minus. We see that this it means that these normal forms of the functions we have in the proposition, the first form does not have any freedom, right? You can, if you chosen this coordinate on the line, it is unique, because if you take another coordinates which is not linear, you will get extra terms, right? Or if it has any coefficient in front of it, then you will get the coefficient here, which is not 1, right? So basically, you cannot do anything here. But if k is even, you can do a coordinate change which will look x into minus x, right? So this is like the some in this case is a finite group action, right? You just flip the coordinate, and we see that this normal form, the corresponding coordinate system for normal form, is not unique. Again, for the first for the odd k it is unique, for even k it's not. but it's okay, it's controllable, it's only two coordinate systems. So we have proven the following theorem. We looked at the classical Nijenhuis theorem, but actually what we didn't, we used our own splitting theorem. And here we look at this and we say that, well, the normal form of the operator we see here, if we again using only coordinates which are centered at point P with non-constant eigenvalues, then the normal forms is governed by the following collection of information. These are CI, these are constants. This is exactly, here we have C, which is without any indices, but here we have lambda 1, lambda 2, so these are corresponding indices. So we have the constants. What is the geometric meaning of these constants? It's just the value of the operator at the point. Okay, what else? We have powers of k, ki, within index I. These are the powers that govern each of the eigenvalue. And we have delta I. These are constant which are 0 or negative 1 or plus 1 for even ki. These are the case we have seen here, case 2 and case 3. Now, we see that if you have this normal form, this normal form is unique. But the coordinate system, the canonical coordinate system, is not unique. But there are finite number of coordinate systems like this. See, basically you need to take, you need to look at all your ki and pick the ones that are even. There'll be s of them, and the number of coordinate systems is 2 to the power of s. This is just the group here. Group action here is trivial. It is a Z2 group multiplied s times. You just again can flip the coordinates. Now, two important comments in the end. We will get to the constant form because it has different value for us. We will discuss it later, and constant form is important. But for now, we need to keep in mind that the difference between constant eigenvalues and non-constant eigenvalues is crucial, because if we look at this, same matrix looks absolutely the same, but lambda 1, lambda 2, and lambda n, they all are constants. And we ask, what are, this normal form is again unique, but we ask how many coordinate systems do we have with this unique form? It turns out that we have quite a lot, infinite number, because any coordinate system, any coordinate change does not change the constant function, right? So that was why we assumed that the constant functions cannot be constant. So if you have a mixed situation, you have constant eigenvalues and you have non-constant eigenvalues. In both cases, you have infinite number of coordinate systems. They are not rigid. You can move them along these directions. This is an important observation, which plays a crucial role in classification problems all over the applications of the Nijenhuis geometry. But again, this is a simple observation. You can understand it easily, but this is what you need to keep in mind. The other thing is that we can allow to move point P. In this case, if we move the point, the constant changes, right? This constant, the CIs, they do change. And we arrived to the problem of choosing the CIs in a appropriate form. This is a problem which is solved according to the given case, right? For example, in some case you can make all the CIs disappear and make all them zeros, and you have a nice polynomial form. For example, for instance, you may have an eigenvalue which is like the lowest. You can try to pick the lowest point. In this case, you will have a minimum of the function plus some x in even power, because it cannot be odd power. This won't be minimum, and so on and so forth. But still, there is more freedom here to kill off CIs, because, well, if they can be made zero, then we have discrete collection of normal forms, right? They're just governed by delta I and ki, right? This collection of functions, which are one of them takes can be only 1 or -1, and the others are should be natural numbers. So these are two important comments. So this is enough with the diagonal form, and we arrive to the diagonalization problem. Historically speaking, diagonalization problem is the first case of application of Nijenhuis geometry, right? Of the Nijenhuis operator, the case when we deal with a sum operator which is not actually Nijenhuis, but Nijenhuis torsion appears in this context and plays an important role. This is how actually the Nijenhuis torsion was discovered. Nijenhuis, his teacher was Schouten, and Nijenhuis was researching the following problem. If you have an operator, right, with the following property, at each point it has pairwise distinct eigenvalues. It can be diagonalized, right, at each point, which means easily you can come up with vector fields, which you will call eigenvector fields, right? Which are just vector fields of eigenvectors at each point, right? But the natural question is, when do these, and if you come up with the eigenvector fields, you come up with the lines along these vector fields, right? So we have like you split the entire neighborhood of a point into the line. You have drawn something which looks like it is a coordinate system. And the question is when it is a coordinate system, right? It's a natural geometric question, because it means that you can pick up a coordinate and make the operator is diagonal. We have seen earlier, like in this lecture, like a couple minutes ago, that if the Nijenhuis torsion vanishes, then you can, in fact, find a coordinate system in which the operator is diagonal. But you will see, we have seen it, that the functions that stand on each point on each point of the diagonal, on each part, on each place of the diagonal, they are specific. They depend only on their own coordinate, xi, right? So the Schouten, he actually solved this problem because he assumed that he didn't try to find any tensorial condition. He was trying to find a condition you can easily check. Easily, we mean you do not need to solve a differential system, any differential equation. That is the main idea. If you can check something using only algebraic method, it is way better if you need to solve a some ODE or PDE. That is the idea, right? Specific examples might vary. So he came up with the following interesting criteria. He said, well, let's take a metric, right? If operator is diagonal at each point, then you can pick a metric, right? Metric tensor, with respect to which the operator will be self-adjoint. Here it is written. And if it is self-adjoint, then when I substitute it into the G, I'll get another metric, H. It is, so you have a pair of metrics, G and H, right? Now you have two metrics. The choice of metric is no way unique, right? There are a lot of metrics that satisfy this condition, but he says, well, pick one, doesn't matter. Still good idea, because what you need to solve is you need to solve a linear system of equation. This is actually the self-adjointness is a system of linear equation. You just solve it, you get the metric, anything, any metric you like, you just pick it. And then you get two metrics. Now, next part, you need to come up with a nabla, which is the Levitt-Civita connection of the metric G, right? It will require some calculations, but still, you do differentiation, but you do not solve any PDEs. Now, you need to calculate eigenvector fields. Again, algebra, you just solve the problem in each point and make the vector fields depend on the coordinate points nicely, right? We will see in later, I have a nice example. It is not a hard problem. Okay, now we have all the collection of the information we need. We need the covariant derivative in terms of Levi-Civita connection of G. We have H, and we have a collection of vector fields. And this is the condition he wrote. So you need to pick up H. You need to take its covariant derivative along the Levi-Civita connection of G. And you need to substitute the vector, the eigenvectors, eigenvector fields. Nice thing here is you need to substitute only pairwise different eigenvectors. So I is not equal to G, is not equal to K. See, the obvious thing which comes to mind if you look at this.
Sorry, what's the H here? H.
H is a tensor which is obtained, here it is, after you substitute L into the G. See?
So what is the definition of H?
Meaning?
Yeah, yes.
It is just a second matrix. If you have two matrices like this, it means that you can take L and it is expressed in terms of matrix like this. You need to take H, you take H, G minus 1.
So this is the definition for H. It is the definition for H by this equation.
I can hear you rather badly. Can you speak louder or maybe bring microphone closer, because I cannot hear the specifics what you're asking.
Okay, so is this the definition for H? This equation is a definition.
I don't understand what you're asking. I'm sorry.
It might be a problem that, so can you hear me? That's Alexey Bolsinov speaking. So the condition, maybe it should be so this expression should be 0, or
yes, exactly, so, it should be 0.
So is this equals 0, right?
Yes, I'm sorry, this typo.
This is a condition on how H evolves. Yeah. Mm-hmm.
Okay, did you receive an answer? Okay, so I will continue. So this is the condition. I'm sorry, this is a typo, right? It should be 0, it's vanished. So, but basically what you note is, if you look at this condition, that it does not, you have no condition, in fact, if you have a dimension 2, right? Because here you in this condition, what you need to take, you need to take at least 3 different eigenvectors. In case of dimension 2, there are no 3 different eigenvectors, at least 2 of them coincide. This is in fact correct, because in 2 dimension, for the operator, if it can be brought to diagonal form at each point, then it can be diagonalized on the entire neighborhood. Okay. So we proceed to the example of non-diagonalizable operator. We start with the simplest possible operator. You
sorry, I'm sorry, one more question. I don't understand where this condition, why this condition, why we write this condition. I don't understand where it is. From what we understand that this condition should be.
If you, there is actually a proof behind this. It's not a condition which is obvious. There's actually a large part of our lecture later will be dedicated to the proving a theorem which is used to prove this condition and both Nijenhuis condition. Okay.
Okay. So thank you.
It's in no way obvious that if this vanishes again, the typo here. Okay, let's look at this operator. It has 3 pairwise distinct eigenvalues, obviously, 1, 2, 3, and it is 3-dimensional for us to have a condition. And we want to prove, we want to understand, right? that this operator is not diagonalizable. How do we do that? Okay, we start with a simple fact. We try to find eigenvectors. They are simple here. The one eigenvector field is the first coordinate vector field, the second coordinate vector field, and we pick the third coordinate vector field in the following form. Again, vector field is not uniquely defined. You can multiply it. So basically we have 3 vector fields. What else? We need new coordinates. Not all the coordinate changes are allowed. It means that we have a vector fields. These vector fields, obviously, they do not define coordinate vector fields in the sense of Frobenius theorem. Why? Because they do not commute, right? It is easy to see that this second and the third, they do not commute, so we didn't find the coordinate system, which obviously because it's you have a non-diagonal operator. Okay, easy. So we need to ask ourselves, what kind of coordinate changes do we allow to make? Okay, as I said, you have a one-dimensional distributions, right? So what you basically can do, you cannot change all the coordinates. You cannot mix them up. You can only multiply your vector fields by some functions, right? And if after this operation, after the multiplication of each vector by some function, they become commuting vector fields, right? Then you apply the theorem we have discussed and you get the coordinate system. It is a necessary and sufficient condition, right? It is a very geometric condition and it is easy to understand. Okay, this is the idea. So we check this condition by hand for this 3-dimensional operator. What do? We multiply by functions f, g, h. We need again, I'm sorry, this is typo here. These brackets should also vanish, right? We write the corresponding bracket, this one, vanishing of this bracket in this form. And we see that we see that we have 2 conditions. We have actually vector field, right? After you take a commutative vector fields, you get a vector field. So you have a vector fields, and vanishing of a vector field means that all the coefficient must vanish, and they must vanish identically. So we see that this coefficient must vanish, and this. We know at the same time that g cannot be 0, right? Because these are the functions we multiply the vector fields. If they become 0, the vector fields become dependent at this point. So there is these functions which vanish. They are no use to us, right? We could have like taken all the zeros and still they commute, but we don't have any coordinate system. Okay, so we see here that g is not 0. Thus, we have 2 equations. The derivative of h and y must identically vanish. And at the same time, the derivative of h and y plus h must vanish identically. So we get that h must vanish identically, which is a controversial, which cannot be happen because in this case the third vector field will vanish, right? So we found the contradiction in assumption that these functions may exist. We just wrote the system and we have seen the contradiction in coordinates, right? So, but to start from this example, we see that this example gives us an idea of what we want. We want to characterize the collections of vector fields, right, which can be made commutative if you multiply them by functions. The next theorem, which we call Frobenius 3, right, because it's similar to the previous 2 Frobenius theorems, this theorem gives us an answer, some sort of bridge to understand how do we get from the coordinate systems and collection of vector fields to some tensorial conditions, right? This is important. So what is the 2 conditions we have? The first condition is the one we are looking for, right? We have a collection of vector fields. They are independent linearly. We have k of these vector fields because we need this statement in general. And we ask ourselves, when do multiplying them by functions we make them commute? Okay, this is the first one. It says that it is equivalent to the following: if you commute any two of these vector fields, their commutator lies in the two-dimensional distribution spanned by these vector fields. So basically what we're saying is that if we take first vector field, if we have three vector fields, right, 1, 2, 3, first, second, third, then we have three two-dimensional distribution like D1, 2, D2, 3, and D1, 3, right? And what we need is for all the pairs of vectors to commute. If we go back to our example, right, we see that the second condition for our example does not hold, because if we take the third and the second and the third vector fields and commute them, we see that we do not stay in this two-dimensional distribution, because we get the first coordinate vector field, right? So this is the theorem we're gonna prove. Okay, I think we're gonna prove it after the break. Let's take a short break, okay? Like 5 minutes. If anyone have questions, please ask.
These two conditions should be for any ij or for some
All the pairs.
Okay, thank you.
Okay, let's go back. Not 5 minutes, but 3. So now we are ready to prove this theorem. This will be an important part of our lecture, like the core part of this thing. So like this. First, step one of the proof is we need to show that the first statement implies the second. Okay, let's take two vector fields for a given A and J and multiply them by functions and assume that the corresponding vector fields commute. Now we need to show that all these two-dimensional distributions are closed. So how do we do it? By the direct computation, we just substitute psi